now that we, I think, understand hopefully mixtures and pure substances better, we understand how to describe mixtures based on their concentrations and whatnot. I want to take a look and see if you guys can answer this question. This comes right out of your book from the Consider This on page 1.1. Remember at the very beginning you were supposed to figure out how much air is in a breath. And you should have recognized that even though your lungs are pretty big, 5 to 6 liter total capacity, you only exchange about 500 milliliters for each breath. So if you guys actually did that, you know, one way to figure out how much air is in a breath is just to blow up a balloon and see how much volume the balloon takes up after you breathe into it one breath. So hopefully you had a chance to do that. But if not, there's about 500 milliliters of gas in each breath. That's the volume in a breath. Now, given that, at normal room temperature and pressure, there's about 2 times 10 to the 22nd molecules and atoms in 500 milliliters of air. Whether that air is inhaled or exhaled air, it doesn't matter. There's about 2 times 10 to the 22nd molecules. That's a lot. And atoms, because remember, in air, it's a mixture that's composed of atoms such as argon, molecules such as mostly nitrogen and oxygen. So then the question here is determine how many molecules of carbon monoxide would be given in that particular sample if the concentration of carbon monoxide was 9 parts per million. Okay, if you have 9 parts per million carbon monoxide in a breath, how many molecules, literally how many molecules of carbon monoxide would that be present in that 500 milliliters of a breath? How are we going to figure that out? Well, okay, if I were to say, now remember, 9 parts per million is just a concentration. And if I say, in that breath, the concentration is 9 parts per million carbon monoxide. What if I said it's 9% carbon monoxide? 9% of the 2 times 10 to the 22nd molecules are carbon monoxide molecules. Would you know how to figure it out? I think you would. If I said it was 9% of, that's the same as taking of is the same as times. So remember, with 9% would have been like 0.09 times that would give me the number of molecules if it was 9%. Well, think of the parts per million in a very similar way. Percent is parts per 100. This is just parts per million. So if I say, okay, if I have 9 parts per million, that's the same as 9 over 1 million of the particles, and there's 2 times 10 to the 22nd particles, or molecules or atoms, I should say, in the 500 milliliters of air. So if 9 parts per million of them are carbon monoxide, how many are carbon monoxide? All I have to do is multiply 9 parts per million times 2 times 10 to the 22nd. Well, how do I do that? You could do it in your head. You could do it on a calculator. But if you did it in your head, just 9 over 10, this is the same as 10 to the 6th, times 2 times 10 to the 22nd. Then that would be the same as 9 times 2 times 10 to the 22nd divided by 10 to the 6th. And 9 times 2 is 18, right? 10 to the 22nd divided by 10 to the 6th, you just subtract those exponents. So that's going to be what? Let's see here. That's going to be times 10 to the 16th. Yeah, because 22 minus 6 is 16. So that's going to be times 10 to the 16th. All right. Now, normally when we report numbers using scientific notation, and that's how this is being reported, we have a number and then a decimal. So to correctly report this number in scientific notation, I'm going to have to move the decimal place over 1. If I do that, move it over 1, then I'm going to have to multiply that's going to be 1.8 times 10 times 10 to the 16th. So I should report this correctly in scientific notation as 1.8 times 10 to the 16th. Oops, whoops, 15th. Oh, great. That was really bad. Okay, so if I'm going to multiply it in proper scientific notation, move it over 1, so it's going to be 18 is the same as 1.8 times 10 times 10 to the 16th. That is 1.8 times 10 times 10 to the 16th is 10 to the 17th. There we go. All right, now if I'm going to report that number, that's fine. There's 1.8 times 10 to the 17th molecules of carbon monoxide in 500 milliliters of air if the concentration of carbon monoxide is 9 parts per million. Now, the next question I want to ask you just by way of review is, did I report that number? I fixed it and I reported it correctly in scientific notation, but did I report it correctly in terms of significant figures or significant digits? Well, if I look at my number of molecules in 500 milliliters of air, I have how many significant digits in this number? I just have 1. The 2 is a significant digit. In the concentration, I have 1 significant digit. It's 9. All right, so in any kind of a multiplication of significant digits, you always have to report your number to the number of digits in the factor that has the least number of digits. Well, they both only have 1. How many significant digits did I report this number to? 1.8 times 10 to the 17th. There's 2 significant digits reported here. So really, if I was going to say how many, given that concentration, given that number of molecules total, what's the number of molecules of carbon monoxide in 500 milliliters of a breath at that concentration? I should really just say 2. Round up to 1 sig fig. 2 times 10 to the 17th. That would be the best way to report that answer.